If we want to go through buffers and talk about them in more greater detail, we have to spend a little bit of time going through what the power of the buffer is. So different buffers will work at different pHs and will work through a different level or amount of buffering capability. The strict definition of a buffer is anything that consumes or releases a hydrogen ion. Again, this helps to stabilize pH. The power of the buffer is related to the quantity of hydrogen ions it can remove. So we oftentimes talk about the blood as being a buffer itself, and there are proteins in the blood that will help buffer pH changes. Hemoglobin is one. Other proteins can be these kind of buffers as well, because remember, a protein has a COO end, so it can bind a hydrogen ion quite easily. So the buffering power of whole blood is right around 25 millimolar per unit of pH. And this is even without bicarb present. So we always have to account for the buffering capabilities of the blood when we are discussing alkalemias and acidemias. Now let's look at bicarbonate specifically. So now we're no longer talking about the buffering capability of whole blood. If we just look at bicarb, we can develop what's called a titration curve. These titration curves are ways that we can deal with how we change pH and then in what form you're going to have the buffer. Is it more likely going to be as a base, or is it more likely going to be in a bound state? So if we look at the curve, we have pH on the x-axis. If we look at the other two y-axes, it goes from 0 to 100 and then from 100 to 0. These two changes allow us to develop the complete curve for this particular equation. The blood is normally around 7.4. The pK is a very important point. At this point, you have 50% that is in this HCO3 minus state and 50% that's in the bound state, which is the H2CO3. This is the operating point in which you could go upwards or downwards. And so we're going to find out that each individual buffer or titration curve that we look at will have a slightly different pK. And we'll talk through why the different pKs are important. But for the blood and for bicarb, the pK in this case is 6.1. This allows us to develop an equation to have us solve for what pH is in the blood. We can take 6.1, which is the pK, plus the log of the bicarb over the PCO2. Now PCO2, we have to also multiply it by a factor, and that is to make sure it gets into solution. That's its solubility coefficient. So you just take the bicarb divided by the PCO2, take the log of that, add 6.1, and that will be your pH.